Okay, so let's go ahead and jump back into it. We are looking at regression, and I would argue this is one of the most important topics of the class in terms of its utilization outside of the class and why your instructors in other departments within the business school require you to take such a class like statistics because of regression, um, especially because of regression. So with that being the case, let's go ahead and go over this example. Some highlights I would like to I'm assuming you read it already. So this is a Boston data set. It's not really housing units, it's just areas of homes. Okay, just areas of homes. Okay, would be our observational unit. And then we're taking a sample of those areas and then we're measuring various things. Such as the average number of rooms within that area, the age, this variable measures the proportion of owner-occupied units that were constructed prior to 1940. So the proportion of those that were made in 1940, before 1940. The distance, or it's the weighted mean of the distance to 5 major Boston employment centers, so on and so forth. This data set is actually a real data set from 1978. Why are we doing 1978 in 2024? Because the data set's easy. It's fine. It's easy for us to learn from. It's also a little famous. So I'll let you finish reading the description and also the variable descriptions. They're a little bit complicated, but we're going to deal with the more simple ones. So when it comes to simple linear regression, this is going to be the first time where our explanatory variable is quantitative. Let me say that again a little bit slower. This is going to be the first time our explanatory variable is quantitative. Okay, so in the past, our response variable has either been categorical for chi-squared sets of independence, but primarily it's always been our two independent population proportions. But for most of the other scenarios, they have all been quantitative responses. This time, both our explanatory variable and our response variable are quantitative. Okay, so here, the average number of rooms, that it is, make sure the average number of rooms per dwelling in the median value income. So MED-V is the median, not income, median value of owner-occupied homes. So it's the value of the home, okay, expressed in thousands of dollars. All right, so these are some summary statistics that are really, really important to have. One of the very first ones is going to be the mean of the X, which is the mean of the explanatory variable, which is the mean of the average number of rooms. The mean of the Y, which is the average number of the value, the average of the value in thousands. So this is like 22,000. Mind you, this is 1978. Standard deviation for both of the variables as well as the correlation. I'm going to speak more about correlation in a little bit, but just note that this is the correlation and it's positive. Okay. Now that we have our summary statistics, it's nice for us to actually visualize the data. The best way to visualize our data of two quantitative variables is to use a scatter plot. Okay. So this is a scatter plot where each of the points represents an observation that has the X and a corresponding Y, an average number of rooms per dwelling, and a median value of the home. Okay, so as we look at this, this has a positive relationship, and that's no coincidence with regards to this positive correlation. Okay, so positive relationship, positive correlation. If this were to be negative, we would expect it to be negative, going down. Okay, so that being the case, we have some values that are strange, which is fine. What else to know here? This red line is the line of best fit. Okay, this line minimizes the distance between each point and the regression line. It minimizes the distance between each point in the regression line. Okay, so now time for the analysis. Okay, so the analysis point, there's a lot of things to mention here, but we're going to come back to each thing in the question, so it's fine. So I'm going to say it, then rewind it and go backwards. And I'm going to reiterate it when I do it. So this point you can ignore. All this you can ignore. The residual final number summary you can ignore. Okay. When it comes to the coefficients, for a linear line, the primary purpose of simple linear regression is for us to create a line or find a line that represents the relationship between two quantitative variables, where we can use x to make predictions on y, or use x to explain the variability on y. So with regards to this particular line, I can use it to make predictions or also explain the variability in my y. With that being said, this line is very important. I need to find this line. Okay, so when it comes to this particular line, my apologies, the line is made up of what two elements? Every line has what two elements? It has a slope, which is what we see the rise over run, and it has a y-intercept when it actually crosses the y-axis. So with that being said, this negative 34.671, that's my y-intercept. This 9.102, that's my slope. Plain and easy. That's it. Okay. We have my standard, every statistic. These are statistics, these are estimates. Statistics and estimates are used synonymously here. Every statistic has a standard error. This column represents the standard errors. This column represents the test statistic. And finally, if I were to do a hypothesis test, which we'll see soon, this will be the corresponding p-values. When it comes to general regression models, we want to we want to know how well they performed, how well did the regression model actually perform in terms of explaining the variability in the response variable. There are two metrics that we want to consider. The first metric is the standard deviation of residuals. I know it says residual standard error, but it's also called the standard deviation of residuals. Okay. And we also are interested in R squared, which is just this, 0.4835. Okay. So just take note of that. We're going to address these things in a few and go from there. These images, I might delete them from your yeah, I'm not going to deal with those. Let's go ahead and answer some of these questions then. So what would be the population of interest? Describe the sample. State the observational unit. So the population would be all the housing unit clusters in the suburbs of Boston, a sample of cluster of housing units randomly selected, and then the observation unit is going to be a cluster of housing units in the suburbs of Boston. Okay, that cluster you probably didn't think of, but when I was mentioning that we're looking at the average number of rooms per dwelling, you have to have a cluster of homes in order for you to get that average. Okay, that's the only way that makes sense. All right, so state the variables in this situation. It's going to be the average number of rooms, as well as the median value of the home. And both of those variables are quantitative. And the response variable is always going to be on your y-axis. Okay, never will I trick you. Okay, so the median value is going to be your response variable, and your average number of rooms is going to be your explanatory. Okay. And they're both quantitative. All right. So these questions are going to get progressively harder. So which you gotta play a game, pay attention. How do we visualize the relationship between two quantitative variables? I already mentioned it. Scatter plot. How do we measure the relationship between two quantitative variables? Now that is where correlation comes in. So the Pearson correlation coefficient. That's the long name. The correlation, the short name, is measuring the linear relationship between two quantitative variables. And we saw that to be 0.6953599. Okay, so the closer R is to 1, or negative 1, the more of a linear relationship it is. Linear relationship. The closer it is to 0, we know that it's just not linear. We don't know, it could be sinusoidal, it could be some pattern, but we just know that it's not linear when R is close to 0. Okay. Okay, so what are some properties of R? So here are some. R is in between -1 and 1. R cannot be a percentage. Okay, so this little element right here is nice. Performing a linear transformation on either of the variables does not impact the relationship between the two quantities. So let's say, for example, I'm just going to make this up. R is equal to 0.54. And that represents a relationship between height, let's say, measured in feet, and weight measured in pounds from a sample of 50 people. If I were to do this again and find the, if I were to use the same sample, have the same sample data, and I had the height measured in inches and the height and the weight measured in ounces of the same exact individuals, OZ, okay, guess what my correlation is going to be? The correlation will still be 0.54. Okay, that's the point that I'm trying to make here, is that regardless, okay, that was a lot. Regardless of the actual correlation, regardless of the transformation, my apologies, it would still be the same correlation. It'll still be the same correlation. All right, so the next thing is to write the regression model from the R output. So that's what I was talking about in terms of the -34.67 and the 9.1. So write the regression model. So what does that exactly mean? That says just write the equation. So yi hat is equal to b0 plus b1 xi. Okay, and then how I can translate that is to yi hat is equal to -34.671 plus 9.102. Okay, that's just the information from our output. Okay, so I like to say regression models have a lot of synonyms. Ordinary least squares regression, simple linear regression model, linear model. I'll try my best to be consistent with the regression model, but know that there's a lot of ways of saying the same exact thing. And so then what it's asked of us is to, write out an interpretation. Okay, so the most generic interpretation for the y-intercept at -34.671 is that when the explanatory variable is equal to 0, the response variable will be 0 on average. Okay, and so how do we do that in terms of our problem? Is like when the explanatory variable, the average number of rooms, is equal to 0, the median home value is in 1K will be -34.671, which is not interpretable because you can't have a home that's valued at -34.67. Nor can you have an average number of rooms being 0. Okay. So you can't interpret that. So make sure you provide your interpretations when it doesn't make sense for you to actually have that 0 value. Generic interpretation of a slope. Okay. When the explanatory variable increases by 1 unit, the response variable would increase by B1 on average. Okay. By B1 on average. So when the average number of rooms increases by 1 unit, the median value of the home will increase or decrease by B1, by whatever the slope might be. And remember, notice I said increase or decrease. So if it's negative, you'll say decrease. If it's positive, you'll say increase. So in this case, since it's positive, it's going to increase. So when the average number of rooms increases by 1 unit, the median value of a home in 1K will increase by 9.012 on average. The on average is key. You need to make sure you say on average. Okay. That's going to be the difference between those who watch this video and just been using ChatGPT, to be honest. There's something else I want to mention. In terms of this line, again, this line has 2 purposes. The first purpose is to make predictions, right? You can say if a random house were to come with 7 cluster of homes were to come with a 7 7 as the average number of rooms in the dwelling, we can predict their the median value of the home. We can also use this line to explain why each of these median values, is deviating from the average number of the average median value. Okay, we explain why it's deviating with this red line. With that said, that's the two purposes. Use the regression line to make predictions, to explain the variability in the response variable using the explanatory variable. And that's just question 5. That's question 4 questions. Let's go a little bit deeper. Okay. So with regards to B0, B1, we can actually calculate these values from scratch. Instead of using the R output and getting 34.67 and 9.10, 9.10, we can actually calculate that by hand. And the equations look like this. Okay, I actually went ahead and just did it for you. B1 is equal to R times Sy over Sx. Sy is the standard deviation of Y. Sx is the standard deviation of X. Okay, and R is the correlation. Okay, you may say, did I give you these values? I sure did above. I'm not going to go back up there for that. Same thing with regards to B0. But notice for B0, it's going to be Y bar minus B1 times X bar. Okay, so you're going to take your means of your response variable, mean of your explanatory variable, multiply it by your slope. So you're going to use this down here to then find your y-intercept. This is a long question. Okay, so it says when the average number of rooms is 7.8. Okay, what is the predicted median value of homes in 1,000s? So what you need to do is take 7.8 and ideally plug it into this equation. But you should be wary. You should always double check to make sure that you have 7.8 is within the min and max of your explanatory variable. Let me say that again slower. Just say it again because you can watch this again. 7.8 needs to be within the min and max of your explanatory variable. Okay. As you can see, it is, so therefore you can make that prediction. When it's not, you should not make that prediction. That's your trying to extrapolate based off of information that's not there. Oh, I got one ahead of myself. So 7.8, you plug it in to the equation, you should get 36.32. However, if the average number is 15.8, okay, average number of rooms is 15.8. You go to 15.8 on the graph, it's not there. So therefore, you can't make the prediction. Okay, 15.8, you can't make the prediction. Okay, so be aware of that. I think the next question, without going down all the way to the bottom, is asking you based on the said median value number, make a prediction on an average number. So you cannot make a prediction on X using Y. Okay, you cannot make a prediction of your average number of homes using the y-axis. All right. With that said, I'm pretty sure that's what I said. We are not able to calculate because we are using the explanatory variable. Rooms is larger than the maximum number. That's part B. In part C, we are not able to calculate the measure because we cannot predict the explanatory variable using the response. That's not how it works in statistics. Okay. All right. So then here, state the non-alternative hypotheses for the slope parameter. Okay. State the test statistic and how it's calculated. State the p-value decision regarding the null hypothesis. Calculate a 95% confidence interval. I don't think we want to calculate a 95% confidence, but let's see. I think we do. Okay. So here, in terms of stating the non-alternative hypotheses for the slope parameter, if the slope were to be 0, would there be a relationship between the explanatory variable and the response? And the answer to that is no. If the slope were to be 0, there will be no linear relationship. So therefore, my null hypothesis is that beta 1 is equal to 0. That there's no relationship. Beta 1 is equal to 0, meaning that there's no relationship. Okay, but clearly we see one, but that's how we state our null hypothesis. Okay, so our null hypothesis would be that beta 1 is equal to 0, and the alternative is that beta 1 is not equal to 0. Okay, just like how we use x bar and mu for the sample for X bar population mu. This is the same thing with B1 and B1 for the sample and beta 1 for the population. Using words, okay, there's no linear relationship between the median value of a home and average number of rooms, and then the alternative is that there is a linear relationship. For us to find our test statistic is actually given to us, but we can actually also calculate it. Our test statistic is going to be 21.72, but how we find it is by taking 9.1 divided by 0.419. That gives us a test statistic. And since it follows a t-distribution, I'm telling you that now, it follows a t-distribution. This is beyond 3.5 and negative 3.5, so therefore we know our p-value is extremely small, and this is our corresponding p-value. All right. I don't know why that's doing that with my camera. Hopefully I'm still being recorded. All right. 21.72. Therefore, we should reject the null hypothesis. Okay. So when it comes to creating a 95% confidence interval, actually I am doing it. Your point estimate is going to be 9.102. Your critical value is 1.96 because I gave it to you in the problem. And then your standard error, which is given to you in the problem as well, 0.419 above, is going to be your standard error. And then here's the math. Actually, an important question right here is that what do you notice about the lower bound, upper bound? What do you notice about this interval? And it's that it doesn't include 0. The 0 is not included, meaning that based on the data, it's not plausible that the regression, that the slope is 0 based on the data. It's not plausible that the slope can be equal to 0 based on the data, which agrees with the null hypothesis. Okay. So again, remember when I was saying how we had to determine how well the model performed, and we looked at these two values, 6.616 and 0.4835. That's what's going on here in this next question. It says in question 8, wow, lights cut off because I've been doing the same thing. So state the standard deviation of residuals. That's going to be that 6.616. What does standard deviation mean, or does it measure? It measures the amount of unexplained variability. Why is this important? Because it allows us to measure how well the model performed. Okay, standard deviation residual measures how far each point deviates from the regression line. So that's what's left unexplained. That's unexplained variability. Okay, the reason why this statistic is so important because it measures how well the model fit the data. Okay. Number 9, we're almost there, y'all. State the R squared. What is R squared measure? It measures the proportion of variability explained by the regression model. It measures the proportion of variability that's explained by the regression model, or the explanatory variable. One of those work. Either the model or the explanatory variable in regards to the response variable. Why is this important? Because it allows us to figure out the proportion of variability that's explained. So here we go. So we have R squared and R. Okay, so I already said that already. R squared is always going to be between 0 and 1. R is the correlation. So if you just take the correlation square, you're going to get R squared. In our situation, we have R squared is equal to 0.04835. Okay, and then the proportion of variability in the median home value in the thousands of dollars explained by the regression model is 0.4835. Another way of saying the same exact thing is that 48.35% of the variability in the regression model, in the response variable, the median home value, is explained by the average number of rooms. Okay, so that is number 9. Let's get number 10. And that was a lot. I know I'm speaking kind of fast. But that's a lot of information. All right, thank you.